And again, each such a magnet has very long coils like this. So each tube contains one coil, one underneath, and this respective electrical currents which flow like this, they also produce magnetic which is vertical. Okay, so again, each coil has two sort of static, but it's increasingly sort of constant magnet. What's stretching or whatever, and it's a short screw.
Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, the radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready, and CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with a target, giving scientists the opportunity to make systematic measurements. Operation of the ESC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. 2 D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electron as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the 2 electrons. The protons are now attracted to the opposite electron and gain more energy. This process is repeated over and over again. Every time the protons make a 1/2 turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1957, young scientists from all over Europe arrive. Among them are Maria and Giuseppe Piccaro. Giuseppe wants to study a short-lived particle called the pion. In 1957, there was a mystery surrounding the pion. Theory predicted that a direct decay into an electron and a neutrino should happen, but this has never been observed.
Phenomenology, only later on in 1957, when we did the idea of the intergovernmental.
In the beginning, which reduces to 60 million times per second. But these two houses or D-shaped electrons are placed inside a big chamber which is behind all this stuff, and this big chamber in fact starts where this ray with the black and yellow stripes ends, and extends to that side as much as the distance between this and that ray, same color structure. Of the apples were allowed underground and assembled, so respectively, since the apples detector there underground of this building, so that means also the LHC also under this building, it runs like this, so 27 kilometers, let's say, okay, and the building here, the ones also behind, also all of this on this area contains different infrastructure related to the apples experiment. Among them mostly cooling, because different pieces of the detector are kept at different temperatures. So some of them at minus 268 degrees, some of minus 180, some minus 95, but that is a different kind of different cooling system. And also in addition, if we have also some relatively small computer let's say clusters in order to read out of the data easily. But other things, so when it decays into two particles, these particles you can detect. But the problem is, so first of all, let me say, so the Higgs boson can decay into two electron or anti-electron, muon or anti-muon. So the muons are particles in some sense similar to the electrons, but have heavier mass, larger mass. Anyway, or otherwise, the Higgs boson can decay into photons, and there are also other different options. Here, physicists analyze the cases when the Higgs boson decay into the photons. The thing is, if your detector registers this photon, it measures the energies of these two photons, and also when you know geometry of the detector, you can also measure the angle between two photons, how they came, so like this. And having this information, by applying special formula, you can reconstruct original mass of the particle. It's from one hand very easy, but the problem is that you have these two photons coming not only from the decay of the Higgs boson, but from the decay of many other different particles, and much worse to that, you have a lot of two photons coming as radiation of two other different charged particles. And that means when you reconstruct original mass, the far majority of this reconstructed original mass in a very wide range of masses will be the particles coming from two photons which are not the same particles, so they're sort of fake masses. But still, if you plot all of these reconstructed masses into one single pole, what is called histogram, because an example of histogram, here we have this reconstructed masses in some special units called giga-electron volts or billions of electron volts in this range. And here what we do is, for example, in the mass range from 100 to 101, you get so many particles with this mass in this range. In the next range you get so many, etc., and you build such a plot. Known particles, so with the exception of Higgs boson not shown, but still it is here. So these particles are, as you see, are called leptons, these are called quarks, and the interesting features of this, they have all charge like electron minus 1 electron charge, while these are neutrinos, particles have no charge, and the interesting thing about this, they traverse practically with the speed of the light, and until recently, physicists believed that they all have no mass, but it turns out they have mass. The interesting way how the physicists discovered they have mass is the following. It turns out that the physicists were measuring number of these neutrinos coming from the sun. It turned out the number of these particles counted in the experiments turned out different from what we expected from theory. And it turns out that on the way of the traveling, one type of these neutrinos is switched into other type. It's like something, if you have apple in your hands and I want to throw you, I throw 10 apples, and out of 10, some of you get something 8, 7 apples and 2 pears, not all apples. So they, while are fine, turn into other fruits. So it cannot always have to pre-accelerate them and to inject into the LHC pre-accelerated particles. And the pre-acceleration, let's say, chain contains from 4 steps. The first one, a starting point, is so-called linear accelerator. Linear accelerator is an accelerator of straight line where it has many modules, and currently it is called LINAC 4. And from 1978 until 2018, it was called LINAC 2, and LINAC 2 was accelerated immediately protons. While this one starts accelerating not protons but negative charge hydrogen ion, which allows to have higher energies and higher let's say properties. Anyway, so when you done. So the final energy here is 160 million electron volts. And then before you inject them into the second stage, which is called booster, you pass them through aluminum foil, which removes the electrons, and you have directly protons injected into the booster. And the third stage is proton synchrotron, the device which was mentioned in the previous film, and the device which built 1959, still not just in operations, but also part of the LHC acceleration chain. And this device can further accelerate proton to 25 billions of electron volts, and then you inject them into this device, which is called super proton synchrotron, and which was built 1976, and in 1980s it was turned into super proton antiproton synchrotron, which was allowing to accelerate not only proton but also proton antiproton, again circular wise as LHC, and collide them in such a way.
The Atlas experiment is a complex machine the size of a 10-story apartment building, and it took over a decade to construct. It is made up of several layers of detectors, each designed to study different properties of particles. Monitoring this complex experiment and analyzing the data is a global collaboration of scientists. With research teams on every populated continent, the Atlas collaboration is one of the largest scientific efforts ever accomplished. Whether they are at CERN or at a research institute abroad, Atlas members work together to analyze LHC data, operate the experiment, and even construct matter to better understand the rules behind their behavior. These measurements and discoveries have advanced our collective knowledge of the universe. While our understanding of the subatomic world has advanced rapidly over the past decades, there is still a lot left to discover. The standard model describes ordinary matter, but that only accounts for 5% of the known universe. The rest is made up of dark matter and dark energy. But what exactly are they? Atlas researchers are looking for new particles and forces that could explain these mysteries.
Although I see a few bunches injected, but they are not for further physics studies. Anyway, when it is in normal operation, so the detector has to be followed carefully. There are many. So the Atlas detector is made of more than 90 million so smallest pieces, or otherwise without channels. And in order to make it easier to follow all of this, you somehow accumulate information. And one of the ways is, you see on the right-hand screen here, the Atlas detector is shown in green color. Green colors mean all information about the status of the detector is assembled and shown as a green, let's say, color, to make it easier to understand if it's in good state. If something is in bad state, it would be shown in red color, and you immediately see which piece of the detector